Welcome to this coding problem walkthrough. Today, we'll explore LeetCode problem number 2175. While the exact details of the problem are unavailable, we'll focus on building a general framework for tackling challenging problems effectively. Let's dive in. It seems that the details for LeetCode problem number 2175 are not accessible at this moment. Please ensure you have access to the problem on the LeetCode platform. If you can provide any specifics about the problem, such as its title, description, or examples, I would be happy to help create a detailed explanation or solution walkthrough. For now, I recommend visiting the problem directly on LeetCode to obtain the necessary details. When tackling a new problem, it's helpful to begin with a systematic approach. The brute force method is often a natural starting point. Here, you focus on directly simulating the problem requirements, iterating through all possible inputs or combinations to evaluate each case. For example, if the problem involves arrays, brute force might involve testing all subarrays or permutations to find a solution. While this approach is straightforward and guarantees correctness, it's computationally expensive, typically having a time complexity of n squared, or worse, depending on the size of the input or depth of the iterations involved. This makes it impractical for large datasets. To overcome this inefficiency, an optimized approach becomes essential. By identifying specific patterns or utilizing appropriate data structures, such as sliding windows or binary search, you can significantly reduce the computational overhead. The key here is to eliminate redundant calculations or pre-compute values to streamline the process. However, these optimized methods often require a deeper understanding of the problem and can introduce additional memory usage, such as hash maps or dynamic programming arrays. The trade-off, though, is a much more manageable time complexity, often reduced to n or n log n. Another strategy to consider is the heuristic or greedy approach, which can be particularly effective for problems where decisions are made incrementally. In this approach, you focus on making the best local decision at each step, with the goal of arriving at a globally optimal solution. For instance, this method can work well for problems involving maximizing or minimizing quantities. The intuition here is to prioritize the most promising candidates at each stage, which often results in a time complexity of n for iteration-based problems. However, the applicability of this approach depends on whether the problem satisfies the greedy choice property, meaning that making locally optimal choices leads to a globally optimal solution. Without this property, greedy methods can fail, especially for problems requiring a broader, global view of the solution space. Therefore, it's important to carefully evaluate whether a greedy strategy aligns with the problem's constraints and requirements. When deciding on a strategy, it's helpful to consider the type of problem at hand. For example, array or string manipulation problems may benefit from techniques like two-pointers or sliding windows. Problems with overlapping subproblems might call for dynamic programming, while graph-based challenges might require traversal algorithms like BFS or DFS. Mathematical or combinatorial problems often involve simplifying the problem using established identities or patterns. The ultimate choice of strategy depends heavily on the problem constraints. If the input size is small, such as n less than 100, a brute force approach may be sufficient and easier to implement. However, as the constraints grow, an optimized or greedy solution is typically necessary to meet the problem's time and space requirements. The goal is to balance simplicity, correctness, and efficiency. Each approach has its trade-offs. Brute force provides a reliable baseline for understanding the problem but is inefficient for larger inputs. Optimized solutions offer significant improvements in efficiency but may require additional memory and careful implementation. Greedy solutions are fast and elegant but are only applicable when local decisions reliably lead to a global optimum. Ultimately, understanding the problem's constraints and edge cases is critical. This ensures that the chosen approach not only solves the problem but does so within the given performance limits. By weighing these factors, you can confidently select the most appropriate strategy for any given challenge. To get started with solving any algorithmic problem, the first step is to fully understand the problem statement. This means carefully analyzing the inputs, outputs, and constraints given in the problem. For instance, you should identify whether the input is an array, a string, or perhaps a graph, and determine what kind of output is required, like a boolean, a specific value, or a structure. Additionally, Pay attention to constraints such as time or space limits and the range of input values. For example, if the task involves detecting duplicates in an integer array, understanding these details will help you frame the problem clearly. Once the problem is understood, it's useful to think about the naive approach. This is the simplest, most straightforward way to solve the problem, even if it's inefficient. For instance, in the duplicates example, you could compare every pair of elements using nested loops, though this would result in an n² complexity, something we'll aim to improve. Next, we can explore optimization by leveraging appropriate data structures. In this case, a hash set can significantly reduce complexity. The idea is to use the set to track elements as we iterate through the array, allowing us to perform fast lookups. Let's break this process down further. When using a hash set for optimization, the steps are straightforward. We initialize an empty hash set, then iterate through the array. For each element, we check if it's already in the set. If it is, we immediately return true because we've found a duplicate. Otherwise, we add the element to the set. If the loop completes without finding any duplicates, we return false. This approach improves the time complexity to n, because each lookup and insertion in the hash set is O(1) on average. The space complexity is also O(n), due to the additional storage used for the hash set. After designing an optimized solution, it's essential to handle edge cases. For example, consider scenarios like an empty array, a single element array, or cases where all elements are unique or all are duplicates. Additionally, testing with large input sizes helps ensure the solution is efficient under constraints. Finally, further refinements may be possible depending on specific constraints. For example, if the array is sorted or can be sorted efficiently, a two-pointer approach could be used. Similarly, if the values in the array are limited to a specific range, a Boolean array might be a space-efficient alternative. Once satisfied with the algorithm, we can implement the solution in code. Here's an example implementation in Python, where we use a simple loop and a hash set to solve the problem. After implementing the solution, testing is the next crucial step. Run the function on a variety of test cases, including edge cases, to ensure it works as intended. For example, test an empty array, arrays with one or two elements, arrays with all unique values, and arrays with duplicates. The goal is to confirm that the algorithm produces correct results in all scenarios. One of the key insights here is the efficiency of hash sets for fast lookups. They allow O(1) time complexity for both insertions and lookups on average, making them ideal for problems like detecting duplicates. However, this efficiency comes with a trade-off. The hash set uses additional space, specifically O(n). This trade-off is often acceptable for the significant improvement in time complexity. It's also important to keep in mind that constraints can influence the approach. For instance, if the problem specifies no extra space, you may need to consider alternatives like sorting the array or modifying it in place. Finally, never overlook the importance of edge case handling. Scenarios like an empty input, single-element arrays, or inputs at the extremes of constraints can easily break an algorithm if not carefully accounted for. Understanding and leveraging the right data structures, such as hash sets in this case, can make all the difference in creating efficient and robust solutions. The operations in this algorithm are both simple and efficient. We iterate through the array once, processing each element exactly once, resulting in O(n) time complexity. For each element, we perform constant time operations like looking up or inserting into the hash set, thanks to the underlying hash table implementation. An additional optimization is the early exit mechanism. The algorithm stops as soon as it finds a duplicate, potentially saving computation time in cases where duplicates appear early in the array. When analyzing complexity, the time complexity is O(n) as we iterate through the array once, and the space complexity is O(n) due to the hash set. However, there are alternative approaches that may be more suitable depending on the constraints. For example, if the array can be sorted efficiently, a two-pointer approach could achieve O(n log n) time complexity while using O(1) space. Ultimately, the choice of algorithm depends on the specific requirements and constraints of the problem. By carefully considering these factors, you can select the most appropriate solution while balancing time and space efficiency. Unfortunately, the exact details for LeetCode problem number 2175 are unavailable. Without a clear understanding of the problem's requirements, constraints, input format, and expected outputs, it is impossible to produce a valid solution. The provided code structure is a template for a solution class, which you can expand upon once the problem details are clarified. Please provide additional context or the problem description to enable a complete and accurate implementation. This is the Java implementation of the placeholder logic for LeetCode problem number 2175. The method solve mirrors the Python code provided previously, which returns null as the logic is unknown. The class structure follows Java conventions, and the method uses an object type for input and output to keep it generic. Here, we begin with a simple example where the input data is a list containing the numbers 1, 2, and 3. The solve function is called with this input, and during the initialization step, any necessary variables would be set up based on the requirements of the problem. Since the problem statement is not defined, the placeholder logic does not perform any specific operations on the input. As a result, the function directly returns none as the output. This demonstrates the current state of the function, acting as a placeholder without any actual implementation. Now, we examine a case where the input data is an empty list. The solve function is called with this input, and as before, any required variables would be initialized, although this step remains theoretical due to the lack of a defined problem. Given that the input is empty and there is no specific logic implemented, the placeholder process simply ensures that no operations are attempted on the input. The function concludes by returning none. This highlights how the function currently handles edge cases like an empty input by defaulting to the placeholder return value. In this example, the input data is a more complex list containing the values 5, 10, 15, and 20. The solve function is invoked with this input, and any necessary variables would be initialized during the first step, as required by the problem scope. However, since no specific logic has been defined, the placeholder implementation does not perform any computations or transformations on the input. As a result, the function directly returns none as the final output. This example illustrates how the function behaves consistently regardless of the input's complexity, due to the absence of problem-specific logic. To summarize, the examples demonstrate that the function currently operates as a placeholder, returning none for all inputs due to the lack of a defined problem statement. This default behavior ensures that the function handles a variety of inputs, including simple, empty, and complex cases, without errors. Once the problem statement is provided, the function can be updated to implement the appropriate logic, enabling it to process inputs effectively and address specific requirements, including edge cases and varying complexities. In this slide, we're focusing on time complexity, which measures how the execution time of an algorithm scales with the input size, denoted as n. Since the specific problem details for LeetCode problem number 2175 are unavailable, we'll instead discuss some general patterns observed in algorithms. The time complexity is largely determined by the operations performed on the input data. For example, if we iterate over an array of size n, the time complexity would typically be O(n). On the other hand, nested loops, where one loop runs inside another, can result in complexities like O(n²), or higher depending on the number of nesting levels. Sorting operations are another common scenario, often requiring O(n log n) time. Additionally, recursive algorithms are analyzed by examining their recurrence relations, which describe how smaller subproblems contribute to the overall complexity. These general patterns help us predict and optimize the performance of algorithms across a wide variety of problems. Now, let's shift our attention to space complexity, which measures the memory usage of an algorithm relative to the input size. While we don't have the specific code for problem number 2175, we can still discuss general cases. Space complexity is influenced by both the size of the input and the additional memory used during computation. For instance, if an algorithm utilizes extra data structures like hash maps, sets, or arrays, it will generally require O(n) additional space. Recursive algorithms, on the other hand, consume space for the call stack, which is proportional to the recursion depth, often O(d). Conversely, in-place algorithms aim to minimize memory usage by operating directly on the input data, achieving O(1) auxiliary space. Understanding these patterns is crucial for balancing memory efficiency with algorithmic performance. Finally, let's explore the comparison of brute force and optimized approaches, as well as the mathematical foundation of big O notation. Brute force methods often involve exploring all possible solutions, resulting in higher time complexities like O, n squared, or even O, 2 to the power of n, in the worst cases. Optimized approaches, however, aim to reduce this overhead by employing techniques such as dynamic programming, divide and conquer, or efficient data structures, achieving complexities like O, n log n, or O, n. Big O notation helps us quantify these differences by describing the growth rate of an algorithm. For example, a single loop processing n elements is O, n, while nested loops scale to O, n squared. Sorting operations often fit the O, n log n category, and recursive algorithms can be analyzed based on their branching factor and recursion depth, yielding complexities like O, b to the power of d. These concepts provide a strong foundation for evaluating and improving algorithmic efficiency, even when specific problem details are unavailable. One of the most common mistakes in solving coding problems is neglecting to handle edge cases properly. For instance, when working with arrays, you should always consider scenarios like empty arrays, single-element arrays, or arrays with duplicate values. Ignoring these can lead to runtime errors or incorrect results. Another frequent issue is using inefficient algorithms for large inputs. Imagine tackling a problem with a brute force approach that has O, n squared, complexity when an O, n, or O, n log n solution is available. This often results in a time limit exceeded error, especially in competitive programming settings. Misunderstanding problem constraints is another pitfall, whether it's misinterpreting rules like values are positive or overlooking requirements for in-place solutions. These missteps can lead to invalid assumptions or unnecessary complexity. Finally, off-by-one errors and loops are a classic source of bugs, such as iterating from 0 to n instead of 0 to n1 in zero-based indexing. These are subtle mistakes but can have a big impact on your solution's correctness. Overlooking space complexity is another error to avoid. For example, using additional data structures like hash maps or extra arrays when an in-place solution is required can lead to memory limit exceeded errors. When it comes to interviews, it is crucial to thoroughly understand the problem before diving into coding. Clarify any ambiguities with the interviewer, such as whether the input can contain duplicates or negative numbers. Clear communication is equally important. Explain your thought process step by step, especially as you weigh trade-offs between time and space complexity. Start with a brute force solution to validate your logic, then refine it incrementally for efficiency. Interviewers often value seeing how you approach optimization. Lastly, recognizing common problem-solving patterns can save you time. Techniques like sliding window, binary search, or dynamic programming frequently appear, and identifying these patterns quickly can streamline your approach. To deepen your understanding, consider exploring related problems. For example, LeetCode 1, the two-sum problem, demonstrates the use of hash maps for efficient lookups. LeetCode 121, best time to buy and sell stock, is a great example of optimization techniques for achieving O, n solutions. LeetCode 217, contains duplicate, is a foundational problem where hash sets are key. And LeetCode 238, product of array except self, illustrates the importance of space optimization. When approaching problems, starting with a brute force solution can be helpful. While it's often inefficient for larger inputs, it allows you to validate your logic before refining your approach. Optimized techniques, such as sliding window or hash maps, can significantly reduce time complexity to O, n. Sorting can also simplify certain problems, though it usually requires O, n log n time, making it best suited for cases where linear solutions are not feasible. Divide and conquer strategies, like those used for finding a maximum subarray sum, can be powerful but also more challenging to implement and debug. When solving problems, it's important to consider trade-offs. For instance, some solutions prioritize time efficiency at the cost of higher space usage, such as using hash maps. Carefully evaluate the problem's constraints to decide which approach is most appropriate. Another key trade-off is between readability and optimization. Highly optimized solutions can often become complex and harder to understand. Strive for a balance, especially in an interview setting where clarity is valued. However, if the interviewer explicitly asks for further optimization, you may need to prioritize efficiency while still explaining your reasoning clearly. Always aim to deliver solutions that are both effective and easy to follow, unless the context demands otherwise. Thank you for sticking with us. Today, we explored a general framework for solving coding problems, even when details are unclear. Remember to focus on breaking down problems, analyzing constraints, and testing your solutions thoroughly. If you found this helpful, don't forget to like and subscribe for more insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!